Hi there, this is Heath. We're going to look at planar graphs today. Let's get started. Back on the day 17 notes, we were talking about Euler tours and Hamilton cycles. An Euler tour in a graph is a path that goes through every edge exactly one time and starts and ends at the same vertex. And we have this criterion that an Euler tour exists if and only if G is connected and every vertex has even degree. And we have an algorithm, Hierholzer's algorithm, that will find an Euler tour in every graph that has one. So we have lots of information about Euler tours. We have an easy test to check to see if an Euler tour exists, and we have an easy algorithm to find one if it does. A Hamilton cycle is a path that goes through every vertex exactly once. Starts and ends at the same vertex. Does not have to go through every edge, just has to hit every vertex. And unfortunately, there is no simple theorem or algorithm that decides automatically for any graph whether that graph has a Hamilton cycle. We have theorems that work in some cases. We looked at one of them last time. One of them is called Orr's theorem that says if a graph has these properties, then it does have a Hamilton cycle. But it's not a complete test because there are graphs that have Hamilton cycles that don't have the properties that Orr's theorem requires. Here's another theorem. Let G be a graph that is bipartite and has an odd number of vertices. Then G definitely does not contain a Hamilton cycle. We'll go through a proof in a moment, but let me give you an example. If the graph is bipartite and has an odd number of vertices, let's say it has 5 vertices, and it's bipartite, so we can split those vertices up into 2 sets, and every edge goes from one set to the other, then because the total number of vertices is odd, one of the sets will be odd, and one of the sets will be even. And if I were to try to create a Hamilton cycle, I can have an edge that goes from an odd vertex to an even vertex from the odd set to a vertex in the even set. Then the next edge would have to go back to the odd set because no edges connect two things in the even set. Then I could go back down to the even set, back up to the odd set. But because I don't have the same number of vertices in each set, I can't close up the cycle. That's the idea. And so we'll have a proof. Let G be bipartite and have an odd number of vertices. Let the set of vertices be partitioned into 2 sets, X and Y, such that every edge connects a vertex in X with a vertex in Y. Since the cardinality of V is odd, one of these sets, either X or Y, has an odd number of vertices. Okay, either X or Y has an odd number of vertices without loss of generality. Assume it's X. So assume the cardinality of x is odd. Let little x be a vertex at x. Okay. So we've set all this up. Now we're going to set up a contradiction. Suppose G contained a Hamilton cycle. Then the cycle would, because it's a cycle that goes through all the vertices, we can choose any vertex in the cycle to be a starting point, would have an odd number of edges. Starting at x and ending at x. Okay. This means the last vertex or last edge in the cycle ends in x. But since G is bipartite, edges have to alternate between going from x to y and then going from back to x. The last edge in the cycle ends in y, because there would be an odd numbered edge, and the odd edges, 1, 2, 3, 4, 5, 6, 7, odd number of edges down here end in y. So we have a contradiction. And so G cannot contain a Hamilton cycle. Our supposition is wrong. So here's an example of a proof that a graph definitely doesn't contain a Hamilton cycle, but it only works for certain cases. It only works in the case where the graph is bipartite and has an odd number of vertices. We don't know a theorem that works for all graphs. It just hasn't happened yet. But there's a theorem here that or a definition here where we can classify pretty easily, and we'll talk about the classification in a moment. A graph is planar if it is possible to draw the graph so that no two edges intersect except at a vertex. It may not already be drawn that way, it's just that it is possible to draw that way. Let me give you an example. The graph K4, K means complete and 4 means 4 vertices, so it has 4 vertices and every possible edge is part of the graph. This is what K4 customarily looks like. The 4 vertices, the 4 edges that go around it, and then the 2 edges that go around the diagonals. But it is possible to draw it this way, by taking this edge right here and putting it on the outside. And now it's drawn in such a way that edges do not intersect like they did here. And so it's possible to draw this graph with non-intersecting edges. Even if it's already drawn this way, we say this graph is planar. Planar doesn't describe how it's actually drawn. Planar describes how it is possible to draw it. So this graph is also planar. We're going to show it. It's planar because it is possible to draw this graph so that the edges do not cross. What I might want to do to avoid crossing the edges is take one of these vertices and move it over to the other side. So if we move this vertex over here, then we would have two vertices in the middle, the two vertices down here, these two edges, this edge, and then we'll have this vertex over here, one edge that goes to this vertex, and then one edge that goes down to this vertex. And I'm still missing this edge here. This edge goes from this vertex to this vertex. And so I've gotten rid of all of the intersections but one by moving this vertex over here. And so I can get rid of that second intersection by removing this edge and drawing it going around the outside instead of going straight across. And so if I call these vertices A, B, C, D, and E, this is planar because I can place A, B in one column, D, E in one column, C over here in a column by itself. C connects to A and B. D connects to A and B. E connects to B, and E connects to A, but taken a long way around so it doesn't go through anything. And so this graph is planar. How about this graph? Looks like a cube. Is it planar? Is there a way of dragging the vertices around so that the vertices don't cross? And the answer is yes. Let's look at this. Let's take the edges here, call them A, B, C, and D. A, B, C, D form a square. And then take these other edges, other vertices, sorry, call them E, F, G, and H, and put a bigger square. And then we have these edges here that go from E to A, F to B, C to G, and H to D, and those edges just go out here. And now we don't have any crisscrossing edges like this graph has here and here. So this graph is planar. How about this graph? Is it planar? Take a minute, see if you can figure this out. We have these intersections around here that we would like to get rid of. So what we can do is get rid of the square that's in the middle. And move it to the outside. Put a loop here, put a loop here, put a loop here. I'm calling them loops. They're not loops, but put a curved edge here, a curved edge here, a curved edge here, and a curved edge here. And now we can get rid of these edges here. What we have left now is a diamond, this octagon, and then these curved edges going around the outside. And so this graph is planar. Let's look at a couple more examples. How about this graph? Is it planar? It's got a lot of intersections, but the intersections are all caused by edges that go either to this vertex or edges that go to this vertex. What if I took B and flipped it down here so that A connects to these vertices, and then B is down here and it connects upwards to these vertices also. Would that work? Try one more. This one's easy. Is this graph planar? I have to get rid of this intersection and this intersection. And I think I can do that by taking these two edges and untwisting them, or these two vertices and untwisting them. So if I go from A, B, C, D, E, F, leave A, B where they are, take C and D and switch them, then the edge that goes from B to C now goes straight down instead of across. The edge from A to D goes straight down instead of across. And then leave E, F back in their original positions. So there's an edge from E to F, an edge from E to D, but that's now straight up, an edge from F to C, but that's now straight up. I don't have any intersections, and so this graph is planar. But what if we added some more edges to this graph? What if I not only connected crisscrossed here between AD and BC, but what if I also drew the connection from A to F and B to E? Let's look at that example. Is this graph still planar? If I did the trick I tried before, of switching C and D, let's see what happens. We have AB, C and D switch, and so now this edge from A to D goes straight down, this edge from B to C goes straight down. I've untangled some of the mess up here, but now if I leave E and F in their current positions, E and F, the edge from E to D will go straight up, and the edge from F to C will go straight up. But the edges from A to F and B to E would still cross each other. If I switch these and moved F and E this way, then the edges from A to F would be straight down, and the edges from B to E would be straight down. But the edges from C to F and D to E would be crisscrossing again. In other words, there's no way I can place these two vertices to avoid both kinds of crisscrossing. This graph is not planar. This graph has a name. It's called K33. K stands for complete, but in this case, when there's the indicator for complete and there are two sets of vertices, we're saying that it's complete in a bipartite sense, that every vertex in this set connects to all three of the vertices in the opposite set. This vertex connects to all three opposite vertices, and this vertex connects to all three opposite vertices. So how can we tell if a graph is planar? We need one more definition. The graph H is a subdivision of G if we replace paths in H with edges so the resulting graph is isomorphic to G. That is, a subdivision looks like the original graph, except that we've just added more vertices along the paths, along the edges. So H is a subdivision of G. If I were to take this path that goes from one edge, all these different vertices together, and just replace it with a single edge, take this path going through 4 vertices and replace it with a single edge, take this path and replace it with a single edge, then I can simplify the graph and make it look like this one here. That's the idea. And a graph is planar if and only if it does not contain a subdivision of K33, that's the graph that we just looked at, or K5. Turns out that's it. If our graph doesn't contain either of these two graphs in a subdivision, then the graph has to be planar. We're not going to take the time to prove this theorem, but we're going to look at some things we can do with planar graphs next time. All right? Take care.